So here I'll draw a picture. There's two things going on. There's what's going on with x and what's going on with f. So here's x naught, and the x's are trundling in, converging x naught. This is the original delta, and then half of that, a third of that, a fourth of that, a fifth of that. So they're being pushed in relentlessly to x naught. And what's going on over here? F of each one of these things, here's L over here. Here's the distance epsilon. There's a wall here. So f of x1, f of x2, f of x, all of them are stuck beyond the wall. They can't get in to converge to L. So even though this sequence converges, the sequence of function values does not. Hence, we have lack of convergence implies lack of sequential convergence. Or the contrapositive of that is sequential convergence implies convergence, which is the converse of what we originally had. Right? So convergence implies sequential convergence and vice versa. So for the reals, all questions of continuity or convergence can be rephrased in terms of just sequences. So how would you phrase continuity in terms of sequential continuity? Well, what's the definition of continuity? F is continuous at x naught if, what's the condition? For all epsilon greater than 0, there exists a delta of epsilon greater than 0, such that what? Whenever x minus x naught is less than delta, that implies f of x minus f of x naught is less than epsilon. If this is we're saying that the function value is the limit here, which is necessary. Continuous functions are constantly attaining their limits. Okay. So how would you phrase that totally in terms of sequences? For all epsilon greater than 0, there exists an n of epsilon, right? It's an n of epsilon, such that what we'd like to say is that there's a sequence xn that's converging to x naught. N greater than n of epsilon implies xn minus x naught absolute less than should we say delta? And that implies the same thing, f of x n minus f of x naught is less than epsilon. You can say here too that there exists a sequence that converges to x naught, such that if you go out far enough, these things are less than epsilon, any pre-assigned epsilon. That might be cleaner to say it that way. There exists a sequence of points xn that converge to x naught, such that whenever n exceeds n of epsilon, this is true. So here, this is totally in terms of the sequence xn and the sequence of f of xn's, right? This one is totally just in terms of the fundamental definition of continuity. In larger spaces, sequential continuity and regular continuity separate. Oddly, sequential convergence isn't enough to detect limits. spaces. But in the reals, it's just fine. And the usual spaces we talk about, R to the n. People have countably infinitely many copies of the reals. The space we were talking about the other day, the little L2 space, Hilbert sequence space. Spaces like that, you can still use sequential conversions to detect limits and frame continuity. And it's really big spaces. Well, anyway, I hope that made some sense. The takeaway is sequential convergence and regular convergence are the same thing for the reals. Cauchy criteria for uniform convergence. We will need this again for the Riemann. Given a sequence of functions. All defined on, now let's just make it AB. That's what we're going to need for the Riemann. This could be some arbitrary set of real. So all these functions are defined on the compact interval AB. Suppose there exists, let's fix epsilon first. Fix epsilon. Suppose there exists n of epsilon such that whenever n and m are mutually greater than n of epsilon, and it's true that absolutely these two things are less than epsilon for all x in AB. Then what do you suppose? What do you think happens now? Some limit function f exists, and the fn's converge uniformly. So we have all these functions. Here's a picture of this. Suppose this is f1, and this is f2, and this is f3, and f4, f5, f6. And after a while, that's f, the pointwise limit of all these things. See, what's happening is, if you pick a point here, and this is a sequence of values here, 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 right? They converge to this value. At this point, of course, it's a bunch of different values. They converge here. They get this pointwise limit. We would like to know whether the convergence is uniform. What is uniform convergence again? Doesn't have to be greater. I drew it going up. The whole thing could wobble around. The idea of uniform convergence is that you can find an n, capital N, so that whenever you're past that with your function in the sequence, you are within epsilon of the limit function, no matter what x in the domain you make. That's the crucial thing, and that's why it's important in integration theory, because it says to you sort of that everybody is about as well behaved as anyone else. If you have a region where the functions are moving very rapidly, and another where, like this, there's not a lot of motion right here. This isn't a big deal. But sometimes you find a situation where in order to converge pointwise over here, you have to make giant leaps to get there. So you pick an epsilon, and you say, how far out do I have to go to be within epsilon of the limit function? It might be not very far at all where they're all close, right? Because you're almost there anyway. A little bit further along, you may have to go further out in your ends to get to within epsilon of the pointwise limit. But if it's moving very rapidly in a place, maybe you can't go past a specific n and be within epsilon all the way along. That you have to keep reinventing the capital N to get by to be within epsilon if you pick a point further and further.